constructed in a composite particle. Okay? When there is a pair of particles. So what we will learn now that what does it mean for the context of entanglement. Okay? So let us say so first thing to notice. So let me turn. We'll do the revisit the problem of quantum entanglement. First thing to notice that we have constructed two projection operators. Let's say we have constructed also the down version of them, and we also learned to construct how to write down the composite one. Now notice that even though not 0 0, this is 0 0 0 1, and this is 0 0, yeah, or both of them are same. So both of them look same, but they have an important difference that this one cannot act on the B particle and this one cannot act on the A particle. They are projection operator for them. So if I want to write the full projection operator, it has to be written in this way. This one can act, this object can act on the composite state of the two particles. And this is an important idea because we are going to use that now this for all kind of entangled state. For example, we have discussed this at the end of the last class that Charlie prepares the entangled state up down, up A down B, down A, up B. Charlie prepares this entangled state, sends one copy to Alice, one copy to Bob. Right? Then the measurement that Alice can do. Okay? So then we also discussed already that we can know that measurement is measuring up spin in a Stern-Gerlach experiment is a projective measurement. So what Alice can do the P up on this whole thing, right? Now this P up has to be written in this form. So Alice can do a P up A, but cannot do anything to the B part. She doesn't have access to the B part. So the B part has to be an identity. So then action of that, I can write down the action of that on this state and calculate all these things. Right? So everybody got this point?
Yes, sir.
Okay. So this is how I should proceed to calculate things in this entangled state. Okay. So let me just repeat once quickly that we earlier discussed that I can do this P up for a spin half particle and act it on this on any superposition state, like let's say up plus down by √2, and this will project this into the up state, right? That gives you the measurement. So you can also calculate the probability by calculating, let's say, this whole state P up and all. Then you will get the probability of getting this up. Okay? See, I want to play the same game for this entangled state. If I have to do this, I have to construct my projection operator in a way that Alice's operator doesn't measure on the Bob state and Bob's operator doesn't measure on Alice's state. But it works on this composite object, right? Because even though Alice got one copy, right? If I want to know what she will get, I have to act this operator on this full entangled state. Right? And we'll see that when we do that, this will project to up A, down B. We'll see that. And you also know already how to do this calculation. I showed you yesterday how to construct this kind of object. Write down the 4x4 matrix, act it on this 4x1 vector, you will get that. I'll show that also today. Okay? So this is the idea of how you should use this composite vector space to describe this entangled state. So now let's go further and try to come up with a more clear mathematical description of entanglement. And this is something I mentioned you earlier as a passing remark, but now I will show you that entangled state is nothing but a kind of state of composite particles, two or more, that you cannot write in a product form in any basis. There is no smart transformation or anything you can do where it becomes a product. So let's see what does this statement means. So let us say I have a composite set. List of my notes. Let us say I have a state A, which is superposition state. This is up, this is down. Belongs to a Hilbert space H. Similarly, I have a state B. This is A also. These are two completely independent objects, right? Just their own Hilbert space. Belongs to HB. Okay. This is what Alice, a state from Alice's lab. Okay. This is a state from Bob's lab. Okay. And these two states are prepared completely independently without any communication. Okay. This is, let's say, Alice's lab. This is Bob's lab. They prepared these two independent states which has no connection. Okay. Now let us say they bring these two together. Then how do you describe this composite object? Okay, can somebody guide me through? How should I write this down? This is my psi AB. Psi AB is this. And what is this? Just write one more step. Come on, you understood nothing about composite vectors or any tensor product or anything. How should I write down this in terms of this up down? What should I do? Am I connected?
Yes, sir.
Okay. How come nobody knows?
Is it C up A psi
Yeah,
B and
that's
C
all.
down B psi B?
Yeah. So so how does this look like after taking the tensor product? How do I break the, if I break this down, what happens? Just expand this, right? Oh my God. I don't know how come are you reading at all anything at home? You have just come to class and listen, right? This is like, if you go to this classical concert, right? If you go there and listen, then you won't be able to play like that. But here your goal is not just to enjoy quantum beauty of quantum mechanics like a classical music concert or something. Your goal is to able to do calculations. Okay? So do something at home. Don't just show up in class just to listen. Okay? So this object is up up AB. So this up up is AB is shorthand for this, by the way. Up up AB means uh, this is all shorthand I'm going to use. Up down AB means up A down. So if I express this thing, this is C up A, C down B. I'm not writing it in this form, although this is also another way of writing it. This is my form. So if I have two superposition state independently, I want to write a composite, I bring them together and write a composite state of these two particles. This is how it should look like. Okay. Now, let us say I want to also express that an arbitrary state. If I want to express an arbitrary state in this basis, in this composite basis, how will that look like? If I want to write down an arbitrary state in this composite basis, how it should look like? This cannot be that bad. We are discussing this for many days.
It will be a linear combination of the up AB, up down
Right.
AB.
So this is just this. You see the exercise between difference between the exercise what we just did. First one I had to already two superposition states and I brought them together and write the composite one. In the second one, I just wrote a general state in this four-dimensional Hilbert space. Okay. Now, what is the difference? What is the difference between two? If something is written like this is more general. Okay, this of course include this, but this has much more. Right? If something is like this, can it be decomposed into this AB form? Okay, that is the question. Can it be always decomposed in this AB form? And if it cannot, then what kind of state it is? And if it can, then what kind of state that is? That is the question of entanglement. Okay? So the question we want to ask, can we express a generic psi AB in the product form of AB subsystems? Okay. So let us see an example that what does it mean when I say it is impossible to write? There are states where I cannot write this one into this form. Okay. So such a state is simple, the entangled state. So let's take a psi AB, which is entangled, which is up down. Okay. So what is this in this composite basis? Right? This is this form. Everybody understand this?
Yes, sir.
Okay. So there must be a solution if this state, if I can write this. So that means what? That means if I want to write this state in this form, it must satisfy four things. Okay? These four components are for these four bases. Up, down. So what are these four things it must satisfy? C up, down, CP must be 1 by root 2. The second is C A down, C up B must be also 1 by root 2. Then the third condition is C up A, C up B must be 0. The fourth condition is C down A, C down B must be 0. So you have to satisfy these four conditions. If such four CSCB exist, okay, then you can say this thing can be written in such a product form. Right? Now you can easily see such a CSCB doesn't exist. Why? Because if this A up and AB both this is 0, then either up A or up B is 0. Right? If this is true, then either up A or up B is 0. Now, if even one of them is 0, then both of these two cannot be true. Right? Everybody see this?
Yes, sir.
So that means there is no solution. There is no solution for C up A, down B, C, yeah, basically C up and C down. Yeah, C down A, C up B. There is no 4 such C's which satisfy this. Therefore, it cannot be written in a product form. So this is the
So
simple. Yes.
can you repeat this point once again?
Which part from where?
Yeah,
This
just
exercise singlet. Okay. So notice that what is our agenda? We first wrote down, if I have a pair of superposition state, the most general possible pair, and I write down a product of them, and to create a composite Hilbert space that is a product of these two independent superpositions. If I do that, I land on this. Okay. Now, if I have a general state in this 4-dimensional Hilbert space, whose basis is this up, down, down, then this looks like this, most general possible state. Just like I wrote C up plus C down, right? So this is like a superposition state in this 2-dimensional Hilbert space. So this is a superposition state in this 4-dimensional Hilbert space. Now, a generic superposition state in a 4-dimensional Hilbert space, can it be written as a direct product of two superposition state in two-dimensional Hilbert spaces? That is the question. If that is true, then this, anything that can be written like this can be written like this. Okay. The answer is no, that it is not true. A generic 4-dimensional superposition state cannot be written as a product of two-dimensional superposition states. And the example is this. If I start with this singlet state, which is 1 by root 2, 0, 1, 1, 0, and that is, this notation means 0 is the coefficient for this up. So if I want to write it down in this notation, this state is simply this. 0 up AB, which means C up is AB. Then 1 by root 2 up down AB, 1 by root 2 down up AB plus 1 by plus 0 down AB. This is this written in this notation. Now, does it mean there exists a CA and CB like that satisfy this? In other words, can I decompose this C up, C down, C down up, C down into A and B, product of A and B, right? That is the question. That is what the question breaks down. So I know that C up is 0, C up down is 1 by root 2, C down up is also 1 by root, down is 0, and C down up is also 1 by root 2. So these 4, can it be written in such a product form? So in order to see that, we have to write them the product form, and then we observe there is no solution that satisfies this. Why? Because if both of these are true, then either C up A is 0, or C up B is 0, or CA down is 0, or CB down is 0, right? If even, no, at least, so let us say one such solution is C up A is 0 and C down B is 0. Right? If this is an accepted solution, then these two cannot be true, because C up A comes here. It cannot be 1 by root 2. C B down also comes here. This cannot be 1 by root 2. I can choose any other arbitrary pair. Any other arbitrary pair that satisfies this, it always violates the first equation. That means there is no solution. There is no way you can find a solution that satisfies these 4 conditions. Right? So that means there is no way you can decompose these up, down, down, up into A and B. Okay? And that is the simple meaning of saying I am given a state that cannot be decomposed, like that. So this is the most simple mathematical definition of entanglement. Okay? Everybody got this?
yes, sir. So only under entanglement we can decompose it into its as a direct product of two subspaces. But
No, it's opposite. Only if it is entangled, then we cannot decompose. Yes, we cannot decompose. That's the definition of entanglement. Okay? So this is very important, interesting definition, that and one simple recipe of cooking up entangled state is that's why frustrated magnet systems, frustrated magnet. Okay? Why? Because this is a little bit of deviation from syllabus. So let's say I have a frustrated magnet. What does a frustrated magnet mean first of all? So let's say I am given some spins that has to be arranged antiferromagnetically, okay, which is up, down, up, down, up, down. Ferromagnet is all same direction. So this is a ferromagnet. And this is an antiferromagnet. Now let us say I make the system 2D. Okay. Now 2D means if it is a square, so then I can always satisfy this. The rule is all neighboring spins must be aligned oppositely. That is antiferromagnet. Right? Up has neighbor down, up has neighbor down, down has neighbor up, down has neighbor up, and so on. Right? Now, if I try to do that in a triangle, then I cannot do that, right? Because let's say this is up, this is down. Now, what do you do here? Right? What do you do here? So it turns out there are 6 configurations. So this kind of scenario is called frustrated magnet, which means this third spin cannot decide what it will do. So then it will be a superposition of this and this. Okay. So the state will be a superposition of this and this. But these are not the only 2 configurations. There are more configurations. Why? Because there are 6 such configurations. So this is up, down, up. This is down, down, up. This is up, up, down. This is up, down, up. Like that. There are 2 more configurations. I am not writing them. So that means the lowest energy state of this system is all these configurations. All are equally good. They are degenerate actually. Basically, they are degenerate. They have same energy. Okay. So that means the ground state of this 3-spin system is this. With a coefficient, let's say 1 by √6, such that it is normalized. Right. Now, such a thing, this ground state, you can never decompose into a basis that is of A, B, and C, or any other form. It cannot be even this psi AB psi C. It cannot be even this also. So there is no suitable basis where you can do this. Now imagine in a solid state system, in a real material, there are 10 to the power 23 such atoms. And let's say you have a triangular system like this. No, sorry. Let's say you have a lattice like. There are many systems like this. There are paramagnetic salts and minerals which has this kind of a property. Okay, so this is a triangular lattice. Okay, I am drawing it well actually. I should have been drawn like this. This is a triangular lattice. There are systems like this which are like 10 to the power 23 atoms of. This is the macroscopic amount of matter, 1 mole of matter, right? It is arranged like this and forming some crystal. So that means if it becomes magnetic, so they are insulating magnet, as I told you earlier. So then their ground state is a massive superposition because it's a degenerate superposition, a degenerate configuration of like millions of states, and their ground state is a superposition of those million states, and that cannot be broken into this kind of product form. You can never break it. So they are highly entangled ground state of a macroscopic matter, and they have very fascinating properties which we study of it. So these kind of systems are called quantum spin liquids. They behave like, even though the matter is solid, the spins behave like liquid. They don't order. We know that if you reduce temperature, a paramagnet becomes ferromagnet, right? At low temperature, if you heat it up, like even the magnet you have at home, let's say, If you heat it up, it goes away. Magnetism goes away because the magnets, the molecular magnets or whatever the spins are gets jumbled up. It becomes a paramagnet. So this kind of system, even if you cool down, even if you reduce the temperature, they will never order. But that is not the only thing. That is okay. That is one thing that they will not order. But they will also have this kind of highly entangled ground state. Anything that doesn't order is not a quantum spin liquid. For example, a spin glass also doesn't order. If the system has a lot of disorder, it will not order. But that is not enough. So you need more definition. The more definition is this, it has a massively degenerate ground state. And that leads to a entanglement, high entanglement. And this kind of entanglement has many fascinating properties. You can see its excitation. If I see excitation over this ground state, they can be fractional. And that means you can get particles which are like fraction of electron-like quasi-particles. We know electron cannot be fractionalized, right? Electrons are leptons. But in such a many-body entangled environment, electron can behave as if it is fractionalized. And this is a fascinating subject. Somebody can pick it up and try to learn about it. Now, there are many other aspects of entanglement. Okay, so let's move on with the syllabus, and then I will tell you a little bit more about some of this stuff. And the most interesting place where you see them is insulator. I don't know if you have learned it in solid state physics or anywhere. There are three types of insulators. Okay? One is Bloch, one is Mott, another is Anderson. Notably, all of them won Nobel Prize for discovering their own insulators. Okay? So probably in the course you are learning in detail about Bloch insulators, band insulators, right? The kind of insulator, the valence bond conduction band and all. So then there is this Mott mechanism, which is this class. They are insulator. They are all electrical insulators. And then Anderson, which comes because of disorder. So this is Mott insulator, and there is some overlap between mechanism in one and two. Like if you disorder a Mott insulator, what kind of Anderson insulator you get? They are very interesting. Like now you might think insulators, they are dead boring objects, right? Nothing happens there. But beneath the frozen electron, this is what is happening, right? So the electrons are frozen, they cannot jump, they are insulated. Right? But the spins are doing all these things. Right? So, and they can be fractionalized also. So you can get a metallic behavior into this fractional quasi-particle, even though it's an insulator. And you will learn all these things. I don't know if you have not already learned. One classic signature of Faraday surface or metal behavior is a linear specific heat. So now if you have an insulator which has a Mott gap, or like Mott energy regime, and you see, you expect there to be not a metal, right? But experiments is showing a linear specific heat. Then who is carrying that heat, right? So these kind of questions people ask, and they are sometimes used to understand that whether such an entanglement happening. So this is also a very interesting thing to see. This is entanglement is something fascinating happening in Hilbert space, right? Hilbert space, things are product form or not product form and all that. Now let's say you are operating with two speed, you measure one, you compare them, and then you see the behavior, right? But then how do you know if you are measuring, you are given a piece of crystal, a crystal or a solid, right? And you are told that ground state is entangled, right? How do you know that? You cannot do all these experiments. You don't know how you don't have a lens that gives you a view of the Hilbert space, right? What can you do? You can tickle the system by throwing some electron, some photon, you can drive it with the electric field, you can measure current, you can do transport. So how this ground state property, this kind of highly entangled ground state property manifest in what you can do, what you can measure on this, right? That is a fascinating question, and that's an ongoing topic of research. People don't agree with each other. There are like what happens at the boundary of knowledge. People don't agree with each other. It's amazing. So, but these are very interesting things to study. Okay, now we will come back to the question of projection operator and entanglement, and continue on this. Okay. So now let's one more last piece on this entanglement is that how does this entangled state manifest in this description? So we earlier already described that I want to my state is this. Okay. and my projection operator is this, Alice's projection operator. So I can write it 0, 0. So this will look like. Similarly, I'm not writing all this. Okay. So then I can ask this question. So what is the probability? So now this is what I was telling you to do. That let us say I want to ask what is the probability that Alice will get a upspin. How do you calculate that? You will calculate with this. So that is simply 1 by root 2. So just do this calculation, you will get half. Similarly, you can do the same calculation, you will get half. Now, what is the state that this will project on? What will be the state that Alice's state projects on? So after measurement, the state it will get is this. This is the projection operator acting on psi b that will give you the state. Right? Just like you can say that the projection up acting on up plus down, that will give you the state that you will get because of measuring upspin in a Stern-Gerlach device. So also, of course, it has to be normalized. Right? So the normalization is simply this. So if you do this, you will get. So you know how to do this because you have to multiply this and this in the numerator, and the denominator is already 1 by root 2. You know that because we have already calculated this quantity. So you will get 0. If you do this, what happens? Which is similarly, if you do psi prime equal to for the downspin, you get with the same thing. It means down up here. So this is just to demonstrate that this is already something we have seen and know. I am just showing you how to do it using these operators. So I start with this. Alice performs her local measurement and projects this whole system into this. If she gets up, right? So when she does that, when this is AB, this is AB, this is also AB. So that is where is the fascinating aspect of entanglement, which we already discussed. That a local operation in Alice's lab tells her the global information about the state. Right? By performing a local measurement here, I know what is the state in Bob's lab. Right? And why this is different from the sock example? Because the sock example, that is the only possibility. If Alice got up or red or white, the Bob's one is blue. But in this case, it's a superposition, which means it is both up and down at the same time until measured. Now, once you perform the measurement at Alice's lab, the Bob's lab particle knows that a measurement was being done and orients itself, or then it guarantees itself to be the other one. Okay? If it is up, it is down. If it is down, it is up. So this fact violates locality. So that is one of the issue. That is one of the main point of entanglement, and that is what we discussed in the entanglement. I am just showing it using the same. I'm just showing you the same thing using this formalism. Okay, everybody is clear about all this?
Yes, sir.
Okay. So now I will talk a little bit about another thing called partial trace, which is a very useful thing to know when you want to calculate the properties of this kind of entanglement. So this job of projecting into a subspace of a composite Hilbert space, that is done formally with another object called partial trace. So let's learn about that. Okay. This is nothing new, it's just a different way of doing the same thing. So the idea is very simple. The idea is this. In a classical particle, what do you do? Let us say I have two uh, coins, right? And I am tossing them. There are probability of 4 states, right? The states are head, head, tail, 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 tail. Right? Now, each of them has probability 1/4. They are equal type of coins. Now we can ask the question, what is the probability that the first one is tail? The probability that first, so this is first coin, this is second coin, that first coin is tail. How do you calculate the probability? You will sum over that subspace, okay, of this whole subspace, of this whole space, you will sum over that subspace which is tail, right? Tail in the first coin. And that is 1/4 plus 1/4, that half. Very normal thing. You can calculate what is the probability of the first particle being of the first coin being tail is by summing over this configuration spaces that part which is tail. Okay? So this same idea is, and you have seen this idea in many different cases. Like for example, when we are doing this Maxwell-Boltzmann problem of n particles in a box, they are having a velocity distribution. Now we want to calculate the probability distribution of the first particle. Let's say. So then what you do, you will do V1 averaged over the P, V1, V2, V3, all the particles. So then you will sum over all the V2, V3, everything, except, and the V1 will, that will give you the V1's probability distribution. Okay? So this idea, same idea, okay? Same idea we are going to use here. So here also we did kind of, this projection is also kind of doing that job, but not so manifestly. So that is what we'll see now. Okay? So the idea is to sum over that part, that the part you don't know, don't want. So the idea is following. So let us say, so in composite vector, let me do a little mathematical stuff. So tell you how this works to do that in a composite, in a vector space. So let us say I have two vectors, two matrices. One is A11, A12, A21, and B is B11, B12. So then I want to do the A direct product B. And how will I do that is, okay, this is what I do. Now the definition, the mathematical definition of partial trace is following. If I want to take a partial trace over the B sublattice, or sorry, B submatrix or B subspace, then it is given by this. So now I take a trace on this B matrices. Then it becomes A11, This is the trace, right? Sum of this. All of them multiplied by the same thing. So this is this quantity. This is this basically. So similarly, you can do the same thing in terms of by summing over the A sub part. Okay. So this idea, we will use this to do this job on extracting the density matrix of one sub. So let's say I have a density matrix which is of a composite particle. This entangled state. Right? Entangled state is up, down, down, up. Now I want to extract the density matrix of Alice's state. So then what I have to do? I have to do this partial trace. So an Alice's state is what? Nothing but this. Such that it will give me that. And so on. I can do the same job in the other way. Okay? And at the end of the day, it should give me, so let us say, so the idea is the same as before. So let's say I have a composite object. I want to calculate an operator. Its expectation value is trace O rho. So I can rewrite it if this is a product form, it's a product state, then I can write it. Even if it is not a product state, even then I can do it. That I'll tell you. So because there is nothing stopping me from writing the OA operator. The OA operator is still of this form. Now the trace P, if I do this, will do the job of converting into OA. So just like this. And that will give me basically I can calculate the average of O, which is O is an operator that acts only on the A sublattice. Or sorry, I'm always calling sublattice because in condensed matter I'm used to sublattices. So O is an operator that acts only on the A part, right? So I can calculate the action of O in two ways. Either I can take the big O, which is O cross IB, and calculate it trace O rho for the big rho, which is AB, or I can just calculate the it on the A part or only on the A part. But then I need to know what is the correct A, what is the correct rho which I will use it. If it is product form, then it is very easy. But if it is not product, then I have to just take a partial trace. That will give me the A sub part. So if I have a two-part system, A and B, I know the rho AB. How will I get the rho A and rho B from there? That is what this partial trace will do. So let's see this thing in action. Okay? And let's do through one example. That is the basic. Then I will come back to the theory. So my psi is this. So my rho AB is this. Just expand these two. Okay. Now I want to know what is the density matrix for Alice's state. We know Alice's state is a superposition. It's a single superposition. So the density matrix will be So what is the meaning of taking trace B? The meaning of taking trace B is doing this. Up, row AB, up, plus, down. This is B. Right? Row AB, right? So that means I should get this. If I do it on this, so notice what will let me show you for one case, then you will know the case. So let's take this term. So what is this term? Up A, down B. Okay. Up A, down B. That I am putting into up B. So this will give me 0. This will give me 0. Okay. So this term will not give me anything. Okay. So let's take the second term. So second term will continue. Okay. The second term is up A, no, down A, up B, up B, down A, up B. So this will give me down A, down A. Right? I'm simply using the relation that up, up, B, B is 1, up, down. They are orthogonal state. B is 0 and so on. Okay? So this will give me this. So this term will also similarly will give me up and down is different. So this will also give me 0 and this will give me down, down. Okay? So I think I have written something wrong. Up, up, down, down, up, down, down, up. Okay. Yeah. So just carry through this exercise. I think I have written something wrong here. One up or down I have mixed up. I think the fourth term should contribute. Down, down. Oh no! I didn't mix up. Okay. So this will give me only one term, and similarly this will give me another term. The second term that I'll get is this. Okay? Only this term will be non-zero. Okay, everything is correct. So then the row I'll get is this. Which is a identity matrix. So you can now do this in another way, which means you start with this row, which is half 0, 0, 0, 0, 0, 0, 0, 0. You can take the partial trace. Okay. You will get half 1, 0, 0. So try to see this in this way. You can also do it in this way, but also you can do it in this way. But there are two important lessons from here. Okay? One lesson is this row, this thing. This is a mixed state, right? This is a mixed state form. So that means, and easy to check. If you calculate trace row square is less than 1. So that means if I have one copy of a state, it's always a mixed state. Right? So this copy is basically a mixture of up and down, 50% mixture of up and down. And this is one way to prepare a mixed state. That I started with an entangled state, and Bob's version and Alice's version individually, they are basically mixed states. Okay? So now let me do it in more general way. I'm just outlining this. You can do the calculation. So I can write down this thing IA plus JB for any generic pair, not just up down. Okay, this is A basis, A Hilbert space basis. This is B Hilbert space basis. You can write down a row AB, which is psi, and that is nothing but IJKL. Okay. So this side is ij, this side is k. So Cij Kl star, you get I K K. So this is the composite density matrix. Okay. Now you can write the row A part by tracing over the B part. What you have to do for that? You have to compress this thing into something, let's say M. Now this M is only for the B. So this is A, this is B. Let's say this is A. When you do that, the row A you will get is some ik, dik, I only of it. The dik sum over j, pij, ck. This is the way to construct this. So that means that this is, and this is always density matrix of a mixed state, because you are taking this identical pair of states and you are summing them with a number. So that means even if the full system is in a pure state, as far as Alice's copy is concerned, it is a mixed state. Okay? What Alice will get, this is a mixed state. And this also tells you, this is also not very surprising, because this is one way to see that how probability comes because of our ignorance of the other part of the system. In this case, the probability comes because Alice doesn't know what is there in Bob's part. So that's why she is getting a mixed state. That's one way of seeing it. Okay. Okay, so that is all I roughly wanted to say about this entanglement and mixed state. There are actually many more interesting topics, but now I think that's where we'll stop and switch on to a new topic. Many interesting topic means there is a quantity called entanglement entropy, which is an extremely useful quantity to understand how entangled two states are. There are degree of maximal entanglement, less entanglement, all these concepts are there. Two states are entangled, but then there is also a question how entangled. So how do you define such a question and how do you measure that? So there are many interesting questions to that. And entanglement, let me say a little more about entanglement. This is also not a part of syllabus, just for you to know. So entanglement tells you how correlated are two parts of a system. So the growth of entanglement tells you a lot of things about a system. So last time I told you about this MBL, right? So MBL means a system is localized in Hilbert space. It's not well connected with the other part of the Hilbert space. So then you can show that if I divide a system into two parts, A part and B part, okay, and measure how entangled A and B are. Okay. Now, if this system has only local interaction, long range, short range entanglement, local interactions, right? Local correlation, not interaction, local correlation. So then only the particle here, the object here, the part of states that are here in Hilbert space will not be connected to a state here, right? So, but they will be connected only to the state its neighbor, it's next to it, right? So then you can show that that means if I calculate the entanglement of this part, this sub part of this system, of this composite system, so this guy is only connected to this guy is only connected to this guy is only connected to this guy. So it's only the boundary, right? So then you can show the entanglement grows as area. So area is boundary of a region to other. So this boundary is always one dimension lower than the actual system, right? If it is a 2D, I have drawn this picture in 2D. So the boundary is a one-dimensional object. In a D-dimensional system, the boundary is a D minus one-dimensional object. In a 1D, boundary is a point, right? Boundary is a point object. So entanglement, when it grows as area, then it's a sign that this system is locally correlated, not globally, which means it's like an MBL. But if this point is connected to this point is connected to this point, connected to this point, then as you grow this system, this A, then the entanglement will grow as the volume. So this area law and volume law of entanglement are two of very strong signatures of how correlated a system is in its Hilbert space. So often in this frosted magnet and many cases, you calculate the entanglement by dividing the system into two parts and calculate it for one part and see that how it grows as you increase the size of that part. And then there are many other interesting questions. Then of course one asks, how do I know how entangled it is? Then there is this quantity called entanglement entropy, which tells you that it is written as rho ln rho, trace of rho ln rho. It's just like your sorry, this is entropy is S. Entropy is S that goes as trace rho ln rho. You can take it up as a term paper and all that. And there are a lot of information. So if the ground state, for example, is non-trivially topological, then you can see the entanglement has a term that shows that. And there are many other fascinating points. Like, for example, how do you define entanglement for systems that cannot be easily divided into two parts A and B, like long range interacting system or systems that have gauge bosons, okay? Or even bosons. Even for bosons, it's a tricky question. How do you define? How to define and calculate entanglement? Okay? So gauge bosons is another. Gauge theories are anyway non-local, right? They are non-local objects. So they have these loops and all that. So these are all very interesting challenges that, like, generally it's not always easy for any system to split them into two parts. There is no well-defined and nice way to do that. Okay, then it becomes a problem. How do I define entanglement? How do I calculate? How do I figure out its area law, volume law, and so on? So these are all the cool things. That entanglement is one of the, I would say, one of the main hallmark of quantum mechanics. One is superposition, of course. Another is entanglement. It has no classical analog anywhere. Even mathematically, you might find superposition. For example, you know vibrational mode of an atom or a vibrational mode of strings as superposition. Although that superposition has nothing like quantum superposition, because quantum superposition has this measurement collapse concept. And there the superposition means it's two things at the same time until measured and all. They're very different. But at least mathematically similar, that superposition, how you work with it. But entanglement has no counterpart. It's the most strange thing. And that's why I showed you in this slide, right? Somebody said entanglement is the most important discovery, etc. Okay, that is all I wanted to say about this chapter. But you should be technically well versed with all this kind of calculation, at least in this course. And these interesting aspects of entanglement that you can take up as a term paper, okay? or your own reading. So that's all I wanted to say about this part. From Monday, we'll start a new chapter of describing multiple particles, the quantum mechanics of multiple particles. That's all. So that's all from my side. If you have questions, you can ask, or we close this class. Okay, good then. See you on Monday.